Hey guys, today we're going to determine ions in compounds. We started to explain this last week when we were looking at a compound and how to dissociate it into its ions. And I noticed that you guys were struggling just a tad bit. So we're going to go ahead and do kind of a whole lesson on it because it's very important to know how to do that for this chapter. So in this chapter, we're going to learn how to write complete double replacement reactions. And we're also going to learn how to write net ionic equations. And in order to do this, you have to understand what ions make up a compound and how to dissociate them and separate them. So in order to understand how to dissociate ions, you first kind of have to understand how ionic compounds are formed and how ionic ions get their charges. So if we're looking at monoatomic ions, mono means one, and then atomic means atom. So ions made up of one atom. We're going to first look at cations. So cations are positively charged. Hopefully you remember from the beginning of the semester, we did recover that metallic elements tend to lose valence electrons and they form cations or positively charged ions. In that lesson, we learned that all the group 1A ions have a 1 plus charge. Everything in group 2A have a 2 plus charge, such as magnesium and calcium. And aluminum has a 3 plus charge because it's losing 3 electrons. So if we were going to give the key idea, the one thing that you should write down, here I'm starring because this is going to illustrate exactly what was on the last slide. When metals in group 1A, 2A, and 3A lose electrons, they form cations with the positive charges equal to their group number. So again, 1A has a +1, 2A has a +2, and 3A has a +3 charge. Now if we look on the other side, anions. Anions are negatively charged. So recall that non-metallic, so non-metals, tend to gain electrons to form anions or negatively charged ions. So for example, things in group 7A have a -1 charge because they have 7 valence electrons. They only need 1 more to get to 8. Things like fluorine, chlorine, bromine, and iodine. Group 6A have a 2 negative charge. And then the first 3 elements in group 5A tend to form ions that have a 3 negative charge, such as nitrogen, phosphorus, and arsenic. So just like the last one, this is what you should write down because that summarizes exactly what I've said on the last slide. The charge of any ion of a group A non-metal, is determined by subtracting 8 from the group number. So again, that's groups 5A, 6A, and 7A. So what if we have a metal that forms more than one ion? Well, the charges of cations of a lot of transition metals must be determined from the number of electrons lost. For example, iron, it doesn't have just one set amount of electrons it can lose. It has different charges. Iron can have a 2 plus charge if it lost 2 electrons and a 3 plus charge if it's lost 3 electrons. Other cations like tin and lead, which belong to group 4A, can also have more than one common charge. Typically, tin and lead can either have a 2 plus or a 4 plus charge. Now, there are a few transition metals that only have one ionic charge, and when we learned naming all the way back in last spring in chemistry or 2 years ago in chemistry, these don't have Roman numerals. So these are going to be things like silver always has a +1 charge. Cadmium and zinc always have a +2. So I'm going to start that because that's honestly very, very important to know that those two things, even though they're transition metals, do have specific charges. And then we're going to hit on polyatomic ions now that we've hit on monoatomic. Poly means more than one. Atomic means atom, so things that have more than one atom. Unlike monoatomic ions, a polyatomic ion is composed of more than one atom, but like monoatomic ions, they behave as a unit and they can carry a charge. They can carry a plus charge or a negative charge. So here's a list of common polyatomic ions. I've uploaded this PowerPoint so you can always refer to this list, or you can always go back to this video. This list has a lot of common ones, including their charge. So for example, we have nitrate, so it's an NO2, and then it has a -1 charge. Notice that a lot of polyatomics end in "ite" or "ate". There are a few exceptions, and they're bolded on this, such as cyanide, hydroxide, peroxide, and ammonium are going to be the ones that don't really end in "ite" or "ate". Now that we've kind of understand ions and their charges, let's go on to see how compounds are formed with these ions, because once we know how they're formed, we can undo that or uncross them and find out the ions that are in them. So a common method to write compound formulas involving ions is to use this crisscross method. In this method, the numerical value of the charge is crossed and becomes the subscript on the other ion. So remember, subscript is the one on the lower side, the bottom. Notice that when we cross them, the signs are dropped, so there is no a positive or negative down here anymore. Notice that the overall charge is 0. So one thing, let's break that down and discuss what that means. Iron, we have 2 of them now down here with a 3 plus charge, so 2 times 3 gives me a positive 6. Then we add it. Over here, there's 3 oxygen, so that's where that 3 came from. There's a 2 negative charge, so plus 6 plus -6 is going to equal 0. And the last but not least, notice that those subscripts are in the lowest whole number ratios. 2 and 3 cannot be simplified anymore. So Fe2O3 comes from combining the ions Fe3 plus and O2 negative. Now, if you use the crisscross method to write the formula for some compounds, such as calcium sulfide, which is made up of calcium ions and sulfide ions, notice how these both have a 2 plus charge, and when you cross them, you get Ca2S2. However, since things have to be in their lowest whole number ratio, it reduces to CaS. So this is actually going to get a little bit tricky, and this will probably be the hardest part when it comes to uncrossing ions. Now let's talk about using the crisscross method for polyatomic instead of just monoatomic. If you use the crisscross method for polyatomic ions that require more than one ion, which means the number up here that you are dropping is bigger than 1, we like to use parentheses to set off that polyatomic ion from others. Notice that when we cross this down here on the nitrate, we had to put parentheses around the nitrate. So this 2 goes to the entire thing and not just one element. And this 1, we bring it down here. Again, you don't have to write the 1, so we're good. If you use the crisscross method for polyatomics that do not require more than one charge, which means this one is a 1, we don't have to write those parentheses, because if we don't write anything, it's understood to be an understood 1. And then last but not least, if you use the crisscross method for polyatomic ions, can also result in reducing the charges to the lowest whole number ratio as well. So a good example of this is if you use an Fe3 plus, and then you use a phosphate, PO43 negative. If I cross these charges, you would originally get an Fe3 PO4 3. However, since these charges are the same, I have to reduce them. So you would originally get the compound FePO4, and if you take out the parentheses, FePO4 would be your final one. So now that we kind of understand how ions are formed, what you're going to do on your homework is you're going to use these rules in reverse to determine what ions are formed or what ions come from these compounds. So the number one thing you need to do is you need to uncross charges and check to make sure that they are correct. The hint I do have down there is polyatomic ions charge only uncrosses if it doesn't belong, if it's most of the time if it's on the outside of the parentheses. So let's kind of look at an example of this. If I have, let's for example, BaCl2, number one, uncross these charges. This 2 comes up here, and there's nothing here, so it comes up here. That gives me Ba2 plus and Cl -1. Then you have to check, does Ba typically have a 2 plus charge? And you would look on the periodic table, notice it belongs in group 2A, so yes, it does. Then you look at chlorine. Does it typically have a -1 charge? You would look at the periodic table, see it says group 7A, and yes, it typically has a -1. So you guys are good. In terms of the polyatomic ion example, if we were to do these, you can look and see, let's do, for example, BaOH2. If I uncross them, this 2 goes up here. There's nothing written here. So I originally get Ba2 plus, OH negative. We've already said that this one's good. And then when you look at your polyatomic chart, you will see that this has a -1, so that's also good as well. What happens is if you uncross them and you check them and the charges are not correct, that means the charges were reduced and you need to find out what the correct charge should be and then multiply the other charge by that same number. So let's do an example of this because we haven't seen it. For example, let's do BaSO4. If we uncross them, we have a number here. There's no number outside the parentheses, so this is an understood 1. So that splits into Ba plus 1 and SO4 -1. What you need to do is check these charges. Ba is not typically a +1, so that's not correct. If you look at the periodic table, Ba should be a 2 plus. So since we found out that this should be a 2, we take -1 times 2, gets me a -2. So this should actually be SO42 negative. And if I look on the chart, SO42 negative is a correct polyatomic ion. So that's correct. And these two are what it splits into. Let's do another example. If I did, PbSO4 2, if I uncross them, Pb gets a 2 plus charge. SO4 gets a -1. Typically, Pb is one of those ones that we learned in the previous slide can have a +2 or a +4. So we don't know if that's correct. So we're going to look at the other one, SO4 -1. If you look on your polyatomic chart, SO4 -1 is not a correct poly. So what you'll look and you'll see that this should be a -2. So this should be SO4 2 negative. So since this was a 2, we need to take this times 2. So this should be Pb4 plus. So your ions should be the following. And if you recross them, you should get PbSO4 too, just to check your work. So right here, we're going to classify, I did not change this. What we're going to do here is we're going to complete this example, but we're going to nix these rules because I did not change them in the PowerPoint. And what we're going to do is we're going to separate them into ions. So I want you to take the time, pause this video, and try to separate them into ions. Okay. So let's go ahead and try to separate them now. Here, we're going to uncross these charges. Ag plus 1, NO3 negative 1. When I go to check these, this one's good. And then this one is also on my polyatomic chart, so I am good on that one. When I look at number 2, if I uncross them, we get Na plus 1, CO3, because remember that 3 has to stay there. It's a polyatomic, and you only uncross it if it's outside the parentheses. If it's not, then it's just an understood 1. And this is 2 negative. When I check it, sodium belongs in that first group, so yes, it does have a plus 1 charge. And then this is on our polyatomic chart, so it's good as well. Number 3, we've kind of already done it, so hopefully you got it correct. When you uncross it, you're going to get that Pb is a plus 1. SO4 is a negative 1. You're going to see that this doesn't work, and neither does this. So you're going to notice that it should be SO4 2 negative. So 1 to 2 makes me multiply by 2. So I have to multiply the Pb by 2 as well, and you get a plus 2 charge. So good and good. Here, if we uncross them, we get a K plus and Cl negative. When I check it, this one's good because it belongs in group 1A, and chlorine is good because it belongs in group 7A. Okay, at number 5, if we uncross them, we can uncross this 2 out here because it's outside the parentheses. And then the Ba here, so Ba2 plus, NO3 negative 1. If we check it, Ba is good, NO3 negative 1 is good as well. And the last one, if we uncross it, the 3 can uncross because it's outside the parentheses. There's nothing here outside the parentheses because it's understood 1. We get NH4, 1 positive, and then PO4, 3 negative. If we check it, both of these are correct on the polyatomic chart. So how did you guys do? That's the end of today's lesson. Hopefully it made a little bit more sense how to uncross those. And let me know if you have any questions, and I hope you guys have a good day.